So before I start, I want to have a poll first. I'm doing this poll is because of some of the year one students sending me the email saying that on next Thursday at night at 7:30 to 9:30 we have a test, but they said 8:30 that the test started. So I'm thinking whether we need to do something on it. One possible way is to make it a 1 hour test so that you'll be on time to do the registration if needed. Of course, I will cut the question for the 1 hour test. If because I want to make it minimize the make up, right? Because to be fair to everyone, to maximize the fairness, I try to. It'd be great to make everyone do the same. Of course, I'll cut the question, and that would be, I think, would be 6 or 5 questions instead of 9. So that would be the goal. I'm thinking. I mean, of course, I will try to respect your choice. Okay, so it seems give 1 more minute for you to choose. I think 92 have voted. So I guess it should be fine. Maybe I can end the poll and maybe in 10 seconds. No further question. I guess I should end it. I can share. It seems every one of you are not year one student, but I don't know why we have year one student here. They saying that the registration is an issue. So, and some of you are worried about the registration, the first year program, which is, I don't know why you worry, but anyway, in that case, I just make it 1 hour. I probably would have went 1 hour. I also asked other group in the morning, they said they also prefer 1 hour. So I probably make 1 hour exam. I probably cut some questions, and just will be 7:30 to 8:30. So in case you really need to do things, you can do things. So okay, but any question first before we go ahead? If no, then so just to several things administrating first is this Thursday we don't have class, right? Because of the school have a graduation stuff. Okay, so no class. And the second thing is we have a 1 hour exam. Probably I make clear. So how many? Someone asked me is every question have a sub question? Yes. So there'll be well, you can see what happened to the other past exam papers, right? So you somewhat similar to that, okay? But I will cut short, maybe similar to the other exam. So it will be each question may have 2 to 3 sub questions. Yeah. Of course, dividing into sub question is for you to get more sub credit, right? So that would be goal. 1 hour test. So there's no class on this Thursday. And how many questions in the test, I think I will announce it in the Blackboard, but I think 5 to 6, I guess I cut half. I think 5, I guess 5 to 6, because the number is not really meaningful. It depends on how difficult they are, maybe 5 to 6, I guess. Originally 9, that I think I cut half, because there's some easy question, right? So that will be much faster. And the next part is to facilitate, to make sure that your grading, I would ask you also, besides writing on your paper, I would ask you to write you type your short answer into Blackboard too, just the final answer, to minimize the grading problem, because of so you put your final answer on the web, but also you write the step on your paper that you take picture. No, the homework file will be given, but the deadline will be end of this class be given, because I will give the assignment, but it will not be dead until the end of the same as the project, end of semester. Because we've done everything today. Homework file with you will be released, but I don't want it to be due by the end. Okay. I'll give you more time to do it. Homework 5. And next week we will have a quiz. Last quiz, and then next week, the next Tuesday, we have quiz, and also we have a review, or we have a Q&A section. Okay, so that should be the goal, and then we will do the ask you to sign up for the group project. Then I will allow, once you're done, then I will do the time notary. Okay. Okay, any question before we proceed? So this Friday we have a deadline for the homework 4. Homework 5 will be released after today, but we're given until the end of the semester to finish. Same time you submit the final work. Okay. Any question? The past paper, Is already on the blackboard, or you can look at the library. It's already on blackboard. It's on blackboard, right? Suppose. Let me see. Yeah, using a blackboard. Well, no answer will be given. You can ask TA if you have any question, or you can ask next week. I think we can the Q&A section after the quiz. Okay, we can work out some question at that time. But you may ask TA to if you have done something, maybe you can ask TA for that. But TA also very busy, so just don't start with him too many questions. But give a question, and then we can do it in the next week Q&A. Yes. Any further question? If no, then we will start our class. So today's class, there's not too much material, in fact, because we covered almost the main thing. So we will just briefly review everything, and then we go to the Excel, and then we have time, we will go over the whole course again. Or if you have any particular question on the past exam, then probably you can also raise it out. If there's sufficient interest, we can discuss those. Okay. So let's see. I mean, if you have a question. Any question now? So just to, okay, so let's get started. Untitled regression. And just to remind you, what we're doing here is to look at the relationship, and in particular the linear relationship, okay, between education, income, advertising and sales, drug dose and recovery time, and then many things. Okay, regression is trying to study how variables are related. Okay, and of course, it would be great if we cover causality, right? How change one thing affecting another. It can be done in experiment, or there's some time factor, right? You change the advertising, right? And that usually changing the sales is more or less causal, right? Is one cause the other, but less clear for education and income, right? Because the hidden thing, ability, right, is affecting the both, right? And the drug dose and recovery time, also probably you can establish the causality, okay? Because you can control the drug dose by yourself, and recovery time you can observe, okay? So that's why this is the case, but some other cases less so. You cannot easily conclude one cause the other, right? Especially the data you observe they happen at the same time, okay? Or there's some hidden variable here. But anyway, the regression, the data we have in our case is just you have two variables, okay? And there would be data points X and Y, okay? Try to find a line to fit all the points. So that's why you're looking at the intercept and the slope, okay? So here we focus on simple linear regression. Simple means we don't have gamma Z. which will be left for the advanced class, and it's linear. So we are not talking about having a polynomial. Okay, this is not considered. Okay, so that is simple linear regression, and of course these things are important, and for our purpose it's not focus. We focus on the simplest thing first. Okay, is that okay? If there's no further question, then I will just, it's a line, okay? And what we are trying to see is to this, right? It's a line which will be represented by y hat, okay? This is a data, right? It's xy, okay? So the line, as usually we said, x is different from y in the sense that we're looking at the, when we look at the fit of the data, we look at the vertical distance, right? Because you can also imagine that instead of looking at the vertical distance, you can look at the horizontal distance, right? Or you can look at the perpendicular distance, okay? Why focus on vertical is because we said x is the independent variable, right? Independent variable. And y is called dependent variable. Okay? We're trying to use x to explain y. So the accuracy comes from even the x, how well we are explaining y. Okay, so that's why this is the case. And you can see in the big data, right? They would sometimes they use this as the measurement, okay, instead of the vertical distance, but use the perpendicular. But it's not the goal today. We just focus on the simplest version, the vertical distance, okay? And to find the best line, we are minimizing the distance from this one. Okay? Is that clear what we are doing? If this is clear, then we go to the next. So we have a bunch of data and with the line, okay? And there's a distance, okay, so vertical distance, and we're minimizing the distance by finding alpha and beta, okay? And what we have figured out is if we want to minimize the distance, okay, the best way to do is to use this following solution, which essentially said beta is closely related to the covariance of the two variables, okay? But you're dividing with the variance of x, okay? So it's that normalized covariance, right? It's with the covariance. And you do recall covariance xy over, okay? So you may ask how this correlation coefficient related to here, which we will explain that later, okay? We'll explain how this related, but this would be something that actually related to here, right? It's very similar, okay? With some difference. Instead of variance x and y, just variance x, okay? And so if you look at this, right? If variance of x equal to 1, variance of y equal to 1, right? Then this is same, right? Special case, right? So in some sense, if you look at the data, x and y, you normalize it, looking at x, say minus bar might be just x over, rescale it, x over square root of variance x, right? y over square variance of y. Okay. And in this case, you run the regression, the coefficient would be r, right? Because the variance of this guy is 1, variance of the guy is 1. Okay. So in that case, the beta and the r will be the same. Okay. So that's how they're related in that sense. I hope that would be okay. So let's see the next. So again, in the linear regression, just try to minimize the sum of the square difference. Okay. And this is a proof to show you everything here. And then the next part is the classical assumption. Okay. So far, we just fit the line. So suppose we have some assumption like this model y generated by x through this manner. Okay. X are non-random. And errors have mean 0 and constant variance, then correlated. Okay. And in that particular case, okay, we can prove, but we don't, right? But we just say the alpha hat has expectation of alpha, beta hat expectation of beta. Okay, so that is the Gauss-Markov theorem. And the estimated model will be given by the following. Okay. And do note that, just to remind you that this is a y-intercept, and this y-intercept would be only meaningful there's some data around x. Okay, if data is well above x, so this alpha is not so meaningful, right? Because you know data. Later you will see why that's the case, because the prediction error will be huge if you're too away from the mean of the data. Later you will see why I said in this way. And this beta is how much y would change on average when x increased by 1. So this on average is important. And more important is not causality here. Okay, running this regression does not establish causality. You need something beyond the regression to tell you, either coming from the idea that you can control x, right? Either come from other reason that tell you that this is causality. Okay, and to remind you that it is, as again, you run the same regression with the demeaned data, which is you subtract the mean, you will get the same beta. That means that it is asking the regression, the beta is explaining the deviation from variation of y explained by variation of x, right? It's variation is how it varies from the mean, explaining the varying from the mean, right? It's variation of x, which is this guy, right? Whether it's above its mean to explain whether y is above the mean or not. Okay, so that's the idea. Because that is actually the covariance means, right? If you remember, covariance xy is saying that if x above the mean is y above the mean, if x below the mean, y below the mean. This is the same idea here. But we are more precise now. How much is above the mean for x, then you will be y also how much above its own mean. Okay, and how much is represented by the beta. Okay, so that is the goal here. Now, the next thing is the model we have for the regression equation, right? We have three things here, alpha and beta and sigma square, okay? And this turned out to be, this sigma square is can be estimated through this, okay? Again, we're not explaining why. You can imagine this is, the reason is unbiasedness, okay? It's unbiased estimator, okay? How to prove this, we don't prove, okay? You will be beyond the time that we needed to prove it, but this is estimated by that. Okay, this is standard error estimate. This is, you will find this in Excel output. Actually, we mentioned this last class. This Excel output is there. Okay, Excel output give you this number, and you turn out that this is very important number that will be used to tell us how variation of the alpha head and beta head, right? Because alpha and beta head are coming from the data, right? Or coming from this this is a follow a distribution, right? It's a random variable, okay? And this turned out to be, of course, y is also a random variable, right? So that's why the alpha and beta random variable, okay? And how alpha and beta varies depends on sigma, which we estimate depend on S. Okay, so here last class we have shown the variation of the alpha head is given by this, okay? And is suppose the errors are normal, then alpha head also normal, okay? In that case, we can replace sigma by S, right? And then we can do a t-tax, right? So that will be the main thing we want to know, right? Is because once you estimate the model, right? We want to check whether these coefficients are same or different from some number, okay? Usually the A is 0, okay? But it did not necessarily 0 because it comes from your hypothesis, what should be the value you want to test, okay? But usually 0, in the Excel output is also 0, okay? And this is degrees n minus 2. We don't explain why. It's beyond the scope we explain. Okay, so the point estimate, right, will be given. This is the beta. Okay, the point estimate will be just, it's unbiased, right? So that's why you want to estimate this, right? The best estimate is alpha head, right? And we know the variance of alpha, you can replace by the standard error, right? Replace sigma by S, right? Then you have a t distribution, okay? So that's why you want to know how alpha looks like, then it would be, the confidence interval for this will be like the following, okay? So, and the same, you have the beta, okay? Beta head also the same idea here, okay? And similarly, you have the, if you assume normal, you have this kind of structure, okay? And again, this is the most common test you will be doing. Actually, you're testing this one, okay? You can see this, that the beta would make a difference. But usually B is 0. Okay, this is B is 0. The result is directly from Excel. Excel directly gives you this answer. Okay, so this is T degree of freedom n minus 2. I think this is something we covered last class. Okay, so same, you have the interval for the coefficient. Okay, and sometimes why you care about this, right? Because this is, if you estimate demand curve, right? This is slope of demand curve, so that's why you care, right? So is that okay up until now? I guess we just review. No? Yeah, it's okay. So just review. So now we are going to introduce, I guess we don't have time to prove. Here is ANOVA, okay? Remember ANOVA is, old days is a grouping, right? There's a data within two groups, right? how the groupings can help. Okay, so here's really the idea is I can explain the two things, right? Look at the regression data model, right? What we have is the following. So this is the data scatter plot of the data x and y, right? With 1 point x1 y1, x2 y2, x3 y3, a bunch of data here. Okay, and suppose this is data, right? And remember the goal is we try to use y to explain x, or in other words, you use it for prediction, right? And the model we are trying to have is the somewhat like this, right? And this is the y hat model, right? But this model is relying on x, right? So what is the baseline model we want to use is to predict y. The most easiest thing is to look at is instead of y hat, the y bar, right? Y bar is the most natural thing you want to predict y, right? Give you particular value to guess, just use y bar, right? You want to guess how much one guy earned, right? Is you use average salary, right? So suppose you want to ask how much someone work in, say, Microsoft or some company, right? What's the salary you earn? What you do is the average salary in that company, right? That would be your that would be your estimate, right? So, and what we're doing here is the following, okay? So you can easily see that, okay, this is the baseline. So something what is unexplained, okay, want to explain is this guy, okay? This is the something want to explain, okay, is the orange one. And the data you have explained, okay, because we want to use X to explain Y, right? So this is something you want to explain. Okay, maybe I use the color. Maybe use black. No. So this is something you want to explain. So the same X. Okay. So this is something we want to explain given X. Okay. But what we actually explained it, okay, is this part. And what is not explained it is this part. Okay. This part is the total variation okay, we want to explain, okay, and this is part of explained it, okay, because we explain this way, or we say, oh, why so high, because X is above its mean, so Y above its mean. So this is what the explanation, okay, and what is not explained is this part is unexplained. Okay, so you can easily imagine that the sum of the square of the distance will be called SST, and sum of this distance we've got SSR will be sum of square of regression, and this part will be called SSE, sum of squared sum of square error, and turn out to be the formula we are going to prove will be turn out to be very interestingly, even though they're square, actually this they're equal, okay? Very surprisingly, okay? Because it looks like they're adding together, right? But we're looking at the square, okay? A square, the total square, we still can see this relationship, okay? So this is later you will see this related to F test. So that's why it's related to ANOVA. But anyway, okay, let's see definition. Okay, so what the data minus the model we use y bar, right, is something we're going to explain. Is sum of square total. And you take your model minus the baseline, the y bar is the sum of square regression. Okay, and what is not explained by the model will be sum of square error. Okay, and do note that this is if you SSE over n minus 2 is indeed the S square. Okay, so turn out we want to prove this one. Okay, we'll do it rather quickly, and then we'll break. So the proof is rather trivial. So what we do is add and subtract. So this is extra guy. Okay, so just SST is this minus this, but we add and subtract this guy. So why we do this? Because what we are using the following idea: a plus b squared is a squared plus b squared plus 2ab. Okay, so this is a squared. Okay, and then you have b squared here, b and b squared. Okay, and then this is 2ab. Okay, and notice that the a squared, okay, is indeed SSR. Okay, and SSE, this second part b squared is SSE. Okay, so what you need to show, the green part is indeed 0. Okay, but even though without doing this, actually you know it's 0 because the average of the y hat should be same as y bar. So even though without doing it, you know the answer. But let's actually prove this guy. Okay, what we're going to do is to we will try to prove this is 0. Okay, we prove this 0, then we're done. Okay, so because this is already this two part, and another part, we just try to prove this is 0. Is that clear? So how to prove this is 0? Then it's not particularly complicated. Okay, and just here is recall what we try to prove was alpha and beta, alpha beta. Okay, and this is something I want to prove. This is y I had. Okay, we want to prove this. Okay, first you notice that the alpha and the y are independent of I. Okay, so you can, it's a constant, you can take it out. Okay, and as we said, this guy will be 0. Why? This is 0 coming from here. This is y I had. Okay, so y I had is 0. Okay, just to make sure that you know this is coming from here, and this is 0. And the second step will be just left beta xi. Okay, sorry, I should have a beta here. Okay, but this beta can be taken out here. So this typo, it should be beta head here. But beta is limit of I, so this is the case. And now you can see this is 0. So this guy is 0 again. So in case you can't see, this is 0. So 0 minus 0, that's 0. And so that is how you arrive this solution, because of the fact that the condition to derive alpha and alpha beta hat tells you that this whole expression is 0. Okay. I guess no further question. Then let's do the following. Okay. So we'll define the following. This is important. Output from the Excel is R square. Okay. Called R square or R square. It's called coefficient of determination. Okay. That the idea is the portion of the variance explained by the variance of x, right? So you can just go back to the graph here, okay? R square is defined as SSR over SST, okay? It's the portion explained over things not explained, okay? That means that the higher the R square, the better your regression, right? And then because of the fraction here, you will see R square is between 1 and 0, okay? And this, when you have 1, it means a perfect fit. Okay? And when it's 0, then basically it's a, the model is, the regression is completely garbage. Okay, it doesn't really explain anything. So the higher the better, okay? For one variable regression, the higher the better, okay? And remember, you have SSR, SST. SSR can be written as SST minus SSE. So that's, you can rewrite it as SST minus SSE. So it can be written as 1 minus SSE, SST. Okay, so that is the formula that's given in the slide. Okay. So that will be, this is the formula here. That's what I just said. This is the formula. Okay. To repeat, what is R squared is the portion of variation of y explain the variance of x. Okay. It's how good is the fit. Okay. So now we can give you a further interpretation of R squared. Okay. It may come no surprise to you though. R squared is related to the small r, which is correlation coefficient. Okay. Turn out that this correlation coefficient r, you take it square, the small r is the big R. Okay. So although not really used, but if you have R, which is covariance XY, variance X, variance Y, turn out that R squared is same as small r squared. Okay, so for this I don't prove, but for this part we just state the result without proof. But this shows in simple linear regression, R squared is related in this sense. Okay. So I guess I should have a break first. Let's have a break of 15 minutes. Break until 11:37.
书房第二个。
Someone worry about 1 hour exam would be too long to finish, but as I said, I will cut the question by half, right? So it would not be, shouldn't be a big issue. So it will be a shorter exam. So it shouldn't be a big issue there. Because the 2 hour exam will be more questions, but 1 hour exam will be shorter questions. Okay, I hope that kind of ease your issue here. When you do homework, of course, the first time you learn the subject, then you would take more time. But when you are doing your exam quiz, you know some of the question in a similar style or similar question have been asked, so you shouldn't be too concerning. One question asked is SST, SSR. No, must be between 3 and 1. Reason? No, it's below the same. So let me draw the picture. It's square. So this is SST. If you measure, this is SSR. This is SSE. So must be between 3 and 1. So don't worry about the test. We'll cut 1 hour. The question will be cut by half, I guess. So just to remind you, if you were still worried, but and again, you don't need to worry about whether you finish everything. I mean, it's going to be you are going to be judged by how well you're doing, right? Whether you understand. If you try to look at the question in the past exams, right? It's not tricky question. It's most of the questions are very straightforward. So I will follow the same idea. It's not going to be a tricky question. It's a straightforward one. So I guess if you know enough well about the material, then shouldn't be an issue there. Okay. I hope that ease some of the issue in your mind. Okay, I can show you the blackboard since you have a question like this. So, okay, to ease some of you people are still working for exam. So let me really get into. If a time next class we have a quiz, and after that we can discuss some of the exam. But if you have time, but look at the. I mean, I should use your wheel. Sorry, I should wheel as you. So here, Can you see the screen? Can you see my Chrome? So the test here, the past exam is all here. You can just download and then it will be all the exams. So you can just pick up one exam. As you will see, exam is pretty straightforward, right? So one question is not made by me, okay? So there will be some parts, right? And so the question, you have several parts, 3 questions and 4 questions, right? So say this is 2-hour exam, right? But you have 16 minutes for 4 questions, and then you have multiple choice for 40. So it's like 4 to 5 questions, right? Depends on how difficult they are, right? So if you are able to you feel comfortable with this, then you shouldn't be concerned with our test, because I would guess the level will be similar. I don't think with MCQ because of the online nature, right? And also it's open book, so I think it's much easier than that. So that's why I would have slightly 1 or 2 more questions then would be 5 to 6, I guess, because open book, right? Because here you look at the question is closed book exam. So I guess our one is much easier. So that's why I increase a little bit difficulty, a little bit, in terms of number of questions, because you have access to Excel and access to the book and the notes. So I guess I have a little bit. Otherwise, everyone get full mark, then would not be. I cannot. It would be a problematic thing. So that although it's possible that everyone is doing very well, but I have to design slightly. I mean, relevant. Hopefully generate some discussion, but if happen to be everyone is doing so well, then so be it. But I think but for question it would be somewhat in similar nature. I look at the other years these are downloaded by the TA, by the way. I asked the TA to download it from the library, so you don't need to go to library and download. So you can see the question is something like this. Okay, maybe have 1 part or 2 part, then something like that. Okay, I will try to cut it to 5 to 6 questions. Depends on how many parts we have, but yeah. Any question? I hope you don't too nervous about the exam, because it's open book. Also, open notes shouldn't be a big issue. Any question? I mean, I hope that I ease your mind. And then next Tuesday, you do a quiz, and after the quiz, you can ask me the question. Either if there's no question, I will go over. I will just pick up some exam and we just do it together. That will be the goal. I mean, if there's no question, if the question, I answer question. Otherwise, we just go over. Or you can send me, or you can ask me question on spot, or you send me in advance so we can discuss. That was the plan. Any question? And I try to accommodate. Okay. So now we have this. So now we only have actually left few material to cover. So I don't think you need to work too much. So after this, and then there's no more talking for me. So it will be the quiz and then the test, and then you talk. Okay, I'm done with my talking. So if yours is your turn. Maybe too much. I have talked too much, right? So but unfortunately, it's not easy for you to talk because of the online nature. But luckily, I think next semester, you will be having a mix the mode, so you will be able to attend the class in school, much more fun. So what we have here is to give you a result that is ANOVA. Why we learn ANOVA is at the end we want F test. Okay, this F test is asking the test coefficient of the slope. So this is same as the t-test. You may see, but this is 0 here, but we want to see the t-test, right? T-test, okay? A particular case of t-test. Because t-test, you can test B or not B, but here just only test 0. So the question here is, oh, okay. Oh, sorry. My bad, is it? Oh, sorry. Oh, I never saw the PDF. Oh, sorry for the, so let me get back to here. Sorry, I didn't show the PDF. Oh, you can see this is the exam question. Sorry. So friends will ask, so the exam question like this, if you download it, thanks for reminding me. So questions like this, you can see somewhat like 4 questions, sorry. It will be somewhat similar like this style, but there, because of the online, we don't have multiple choice. Same as here. Here you can see have sometimes 3 questions or 4 to 5 questions, and then half of the other multiple choice, and there's here also true and false, so more than that. But you can see the 12 exam, you have 4 to 5 questions, so we'll have somewhat similar, but because open book, I add 1 more. I think I give 6 questions because of open book, it will be much faster to do for you. So a little bit, try to see if 6 questions can generate some distribution. Otherwise, I give 3 to 4 questions, that would be too easy, I guess. So there's some distribution, so that, but don't worry if you, it's not based on your, if the exam is more difficult, then it will mean that even though your marks are lower, then you will still get higher grade. So it doesn't really affecting the, if I accidentally make it very difficult, doesn't really matter. I accidentally make it easy, doesn't really matter. So we can still be able to evaluate how well we achieve the goal objective of the class. Okay, is that okay? Sorry, now we go back to here. Can you see my slides? I'm sorry for the mistake. Okay, so here is the difference is here is we have is a F test for slope coefficient. Okay, so actually we do the t test already, right? The t test is beta equal to B or beta not equal to B here. Okay, but now we have equal to 0 for the t. Okay, and for the beta not equal is a two-tail test, right? T is here. I hope now it's clear how we do two-tail, right? But for F test, same as last class, we only do one tail. Okay, one tail. Only check one tail. One tail F test. Okay, just the right. You reject on the right. Okay, just make sure that you get it for the ANOVA. The F test is on the right hand side. The reason is the above should be bigger than below. Okay, when you want to reject. Okay, so we're not going to further explain why that's the case, but it will be this result. Okay, and this is SRSSE and this F test, and later you will see Excel output. The p-value from here is same as the p-value for the t-test. Okay, which we'll emphasize in Excel. Okay, Excel you will see the ANOVA part. Okay, ANOVA part will be exactly what we have just covered. Okay, just to make sure that you understand what's going on here. Okay, any question? Okay, so what I want to show you, you will see in Excel. Okay, you look at the p-value, the t and the f the same, and then you will also notice the t square is same as the f test statistic, so the same thing. Okay, this will be, we will look at the Excel spreadsheet, we will actually later you will see these two exactly the same. Okay, we'll go to it immediately after we discuss this line. Okay, so why is the case? So let's go to the t test, right? -0 in that case. Okay, beta had -0 and over this one. Okay, and we define the notation sxx and sxy, to simplify notation, beta hat will be sxy over sxx. Okay, so this is what this is. Okay, and SE will be this over this, right? Because variance, if you remember, variance of beta hat, okay, will be sigma square over sxx. Okay, so the standard error will be this over that. Okay, and you cancel this out. Okay, you cancel this and take a square root. That give you this result. Okay, and use t square, everything square, cancel this out, square, give you this. Okay, and okay, and S is given by this. Okay, this definition, right? And what left is to prove this guy is this guy, which we'll prove in the next slide. Okay, but this is SS alpha 1, this is SSE over N over 2. Okay, and this is F, we try to prove T squared as F. Okay, so what left is the numerator, which will be given in the next slide. Okay, I will try to be this one. The proof is not difficult, so I just try to slow down a little bit to show you. So this is this guy, right? Because the y hat is given by this, right? This is the definition. Okay. And the next step is to write down what's alpha. Alpha is this guy. Okay. This is coming from the regression equation. Okay. And the next step then will be, these are the color, sorry. Color blue. This guy and this guy add and subtract, so they're gone. And the beta hat is independent of I, so we can take it out. Okay, and the square is square, so that's why it's sum of the square. This guy. Okay, and this guy is actually sxx, right? And the beta, right? Remember, is sxy over sxx. So beta square will be sx, and then s and s cancel out. So that's why you have this equation. So this is equal to this. That's what the numerator said. Okay, and that's proof why the t square equal to f. Okay, so that's why t square is actually f. And actually, indeed, it hold more generally. Okay. And now let me show you the. Maybe it's a good time to show the Excel first before we go to more technical part. So let's show Excel. So can you see my Excel? Can you see my Excel screen? Okay. So let's create some data. I don't really care what data you create. You can create in your own manner, just random number where you create. Okay. And I just create another column. I just randomly doing something. Okay. The first thing you see this data set, I don't really care how you come up this data, but we just random it up. So what you do, you should have a scatter plot, right? So I just make it smaller. So example like this is more like a line, right? But anyway, we don't want to worry about this part, okay? But you can see they're negative related, okay? So what we're gonna do, okay? What we'll do, we'll use an add in, right? So add in, which what we have is go to data and data analysis, go to data tab, okay, and the data analysis, okay, and then you choose regression and then click OK. So here we have a lot of input, okay, just to remind you how we do this, right? You just click this button, okay, to engraving in the Y, okay. And similarly, you also go to X, engraving in X, okay. And because we include labels, we'll click the label, okay. Then you're almost done. Output range, you just put whatever you like, you just put here, say, okay. Is that okay here? Let me know if you have any question. Let's slow down a little bit because we don't need to hurry here. Okay. Now, this is the output. So this multiple out is not related to us. What we care is this number, out square. Okay. So out square, later we'll see how we calculate, but this is standard error. Okay, R square is something we care. So here it means that 78% of variation of Y is explained by variation of X. Okay, is that clear what it's doing here? And the next part is is that okay? So the next part is something we didn't explain last time, is ANOVA, this part. Okay, this is the part we didn't explain the last class. So let's go over this slowly. Okay. So degree of freedom is this -1. So let me draw it. Annotate this, right? -1 is here, or this n-1, right? And degree of freedom regression, for our purpose, is always 1. The reason is we only need to use one variable x, okay? And in the later stage, not in this class, but other class, you will see it can be more than 1 when you have more independent variable to explain why. But this is what is here right now. And the residual, right, will be the difference between n and this regression is n-1, n-2. Okay, 1 is here. This n-1 is here. Okay. And this is what we call SSR. Okay. And this is SST. Okay. This is SSE. Okay. This over this gives you MS, right? So this is column F over column E. Okay. Just make sure you. Okay. And this is just MSR over MSE. Okay. And the significance of this, right, the p-value, right? So this is F1, degree of freedom 8. Okay. Go to here. And this is 28.408, right? What's this area? Right? You're using the F dot RT. I think this RT. I forgot. Is it this RT? Is with this dot RT, and then you put 28.408, and then you input the degree of freedom, right? Which is 1 and 8, and then this will give you the answer. Okay, and this R square, right, is coming from SSR over SST, right, is coming from this number over this number, right, is 87%. So we explain everything here. Any question about this ANOVA? Any question? If no, I erase what I written down. Okay, I go down a little bit. Okay, so now, as we said, the F test same as the T test. Last time we covered, actually you can see it from here. Okay, you can see this number and this number. Okay, and we also said the square is the same, so T square same as F. So let's see. Okay, so the second thing you can see is this number and this number, you see. Okay, and as I have said, how to calculate this p-value, right? So let's try to show you this is the right thing. This number, degree of freedom, which is 1, the other one, which is 8. Okay, so let me, where's Anthony? Okay, so it just it's coming from, okay, you take this value, this degree of freedom is a one-tailed test. Okay, and here you can see this is way less than 5%. All right, so you will reject the null hypothesis that the slope coefficient is 0. Okay, the slope coefficient is different from 0. Okay, and you can see the coefficient here is negative 1.8, 1.13. Okay, so there you would conclude that there's a negative relationship between these two, right? So that is the first thing you can conclude from here. And how strong this relationship is, we say 80%, 78%. Okay. Is that clear what we are doing? Any question? So remember, what we're doing here is Excel expression is to see, okay, we have this is the main result, right? This is the model we have. And I try to see this model would make sense because this coefficient can possibly come from the data error. So by showing these two are very different from 0, we have some confidence that this is a good one. Okay, but we also look at the confidence interval also, right? We want to look at how these numbers are, right? Which is it's quite negative, right? So it's pretty safe that the negative is pretty strong in some sense. Okay, let me know if you have any question. Okay. If no question, then we go, how do we come up with this? Okay. Someone asked me how to come up with this. Okay. So standard error, let's calculate that together. Okay. So I hope you still remember how to calculate slope and how to calculate intercept. Okay. Let's do it together. Since your question, how to calculate slope. Slope, you can do the slope with directly put in the y, and put in the x. Okay, this will be the slope, and this will be intercept. Sorry, intercept. We're coming from this y and this coming from x. Hope this part is okay, but I just put the formula test here in case you don't. Okay. So this is the how do you calculate the slope intercept? Okay. And how do we get this number? Okay. So we need to get the y hat first, right? Y hat. Okay. What's y hat? Y hat is you have the intercept. I put the absolute address, and you have slope. I also do the absolute address. I have the stars. Then I can times this 15. Okay. Then I have this y hat. Right. And once I have the y hat, I can do these N2Bs. And then I can estimate the error. Okay. Maybe error square to be faster. Okay. That I would need to do is to this, okay, will be y hat minus y square. Okay. Then this is sum of the square. So at the end, I need the other one, the standard error. Okay. Which is this over n minus 1. Okay. Which is 8. And I have to take the square root because this is the just the s square, maybe s square, s square, and se will be the square root of this. Let's see. So this is the sum of square regression of this. Y. Oh, sorry. This is s square is you have to you are summing this guy divided by 8. Is that clear how we arrive this answer? So let me copy the formula here. Okay. So what you do is, this is the y hat, this is estimated 1. Is that okay, Eugene? Then you take a square, and this is the s square. So basically this, and you get this one. This exactly this is the coming from. What's an error? Is this guy? Oh, sorry. Is this okay? So what I do is y hat square over n minus 2, then take a square root. Okay. If no further question, we just finish the class by giving you the 2 extra result. Okay. Now at the end of the day, the model we want to use is actually more or less the end goal, right? We have the model, right? We now establish alpha and beta, right? Whether they're significant or not. Okay. So with the very end, we want to use this y hat model to do our job, is to do the prediction and estimation, right? Give me the x, what should be the y, right? So that is the goal, right? Because we want to use x to explain y, right? We want to predict in some sense, right? Or estimate, okay? So there are 2 levels of prediction here, okay, for each x. So let me have another graph here. So there's 2 levels of prediction here. Let me draw it again. Okay. Just sorry, I'm not drawing it online to save time. So there's a line here. Oh, a line here, and that's some data point. Full data point. Okay. Data point, and this is X. Sorry. This is X. This is Y. Okay. Maybe draw a better one. It's too terrible. Okay, this is X and Y. And the fact that, okay, remember the underlying assumption we have in the model is the following, right? Y is this. Okay. Here, even for the same X, the value of X the same, okay? Due to different realization random term, different Y, okay? So even though we have this model, okay, if we have the same number of same X, okay, the Y will follow, right? Remember Yi, we have the variance of epsilon with a sigma, right? So it will be somewhat like this, right? Even though the realization of the Y can vary, right? The center is here, but it will jump up and down depend on what epsilon is, okay? So here is, we have this idea the same here. This is our model, right? Maybe different from the actual one. The actual one may be other way one, but this is our model. With the model, we have the same feature, right? It depends on the prediction. We also have some not so fixed, right? Because this guy is coming from this, okay? And this have it's a random variable, right? And this guy is also random variable, right? It depends on what you draw, okay? So that's why this y I hat also has distribution, okay? So we want to know the distribution of y I hat, okay? The two things here to ask. One is asking the two response. One is asking the mean response, okay? Given xi, okay? Because equal to some x value, x0, because the value can be changing, the mean also change, right? Because the many different value, the mean also changes, okay? Of course, the mean will mean here, but depends on where you draw, it can be up or down, okay? And also the individual response, okay? So this is the mean response, this individual response. You will see the point estimate the same. You also, your model will tell you the point estimate is y hat, okay? But the variation will be different, okay? Later you will easily see what are they, but don't worry, the math is rather simple, okay? So your model would say how you estimate the mean of y, okay? You use the y hat, right? The easiest thing to do, right? So just basically this guy, okay? Gives you the value of x0, what's the mean response? Will be you predict, what you predict is the line, right? Because the line is a natural prediction, okay? And we will try to show you, I hope probably very quickly. This one, okay? We have the variance of this guy, okay? And this is an error, okay? And turn out that you can see the further away x0 from x bar, the less accurate you are, right? It is more accurate when it is near x bar, okay? The reason why, because the regression line passes through x bar, so near x bar, then the variation is less. The further away, the variation is bigger, okay? So I'm not going into detail of this. I quickly show you the tell you the proof, how we do the proof. So I'm not going to go into detail because of the time constraint we have right now. So very briefly, the variance of this is written as 3 part. So the proof will be variance x plus y is variance x plus variance y plus 2 covariance xy. So this is something we didn't discuss detailedly, so that's why I will skip the proof. Just give you a rough idea. So this coming from here, okay, this is what we have just shown. And this, the numerator is equal to this. This is during the proof, actually we established this already. And this is coming from the result. And this is something coming from the next slide. And you do the calculation, give you this guy. Okay. And remember this one is when you later you will see this with s squared, right? So this you can calculate, this you can calculate, this you can calculate. Okay, so I guess I don't want to go over this, but the main idea here is to calculate covariance of this is to rewrite alpha to rewrite as a linear function of y, okay, and with linear function of y, and the trick is yi and yj are uncorrelated, so the covariance between them will be equal to variance. And since we didn't tell you that how to do, say, ax plus by and cx plus dy, actually, if x and y are uncorrelated, it will be variance of x. Anyway, I'm not going to, maybe I should don't talk about this. So at the end, you can do the proof because we skip the covariance formula. So just believe me, this is true. Okay. So we're not going to prove this part to save time. So anyway, so just accept this is a result and standard error, replace the sigma by S, and this is the standard error. So you may ask why we care about this. It's because at the end they will want to do this. Okay. So here's the model, right? We have a regression model. We come up with estimate, right? For example, we try to predict how sales and advertising, right? So that is the goal, right? Suppose you're the manager, right? You want to see how advertising, your marketing manager, right? You want to see advertising, everything in sales, right? You have a data, you plot the curve, right? So the manager asks you, okay, suppose we spend this amount next month, what will be the sales, right? So the goal is asking to this. And your response will be, oh, this is the model we run the regression, and this would be the goal, right? And of course, this is just a point estimate. You want to give better estimate, right? It's by saying, oh, this is the mean, the expected sales if we spend, say, $10,000 on advertising, right? This will be our sales expected, okay? But you want to be, say, more, you give an interval estimate, give a confidence interval, right? And based on what we just learned, right, SC and T, right, you can draw this, right? You will see, oh, 90%, 95% of confidence that the sales will be between in this amount and that amount. Okay, so that would be the goal what we want to do, right? Because we run the regression, we get the model is help us to do prediction, right? Because this is something the business application we need, right? Because we try to explain they are related, and for marketing purpose, right? You try to see which program will give you which result. Okay, so that's how the regression being used. Okay, I hope that would convince you that is that okay? Because the next one will be actually very similar. Is that clear? Okay. So this one is also very simple. Okay. It's highly related. So individual response, not asking the mean response. Okay. So the idea is the following. Okay. So for individual response no longer mean. Okay. First, we have to look at the prediction error. Okay. So if you got given x0, okay, and y has 0 would be your prediction, right? That would be your prediction due to the point estimator, right? The point estimator, point estimate. Okay. And this is unknown. We don't know that, right? This is unknown, right? And this is the error, okay? This what actually is, but what you predict is this guy, okay? What's prediction error? This prediction error will mean 0, as we have said, right? On average, okay, this is unknown, but this is generated from the data like in this way, okay? Maybe I should add an epsilon here, okay? And I subtract from the model, which is y I had, okay? And this is mean 0, and this is also have Gauss-Markov theorem is this one, and this is also, this is beta. So that means that the prediction error is 0. Okay, this prediction error is 0, means 0. And the variance we prove is like this. Okay, we'll prove soon. Okay, this is the case. Okay. Now, why is it important? We know the prediction error. Okay, the point estimate of prediction error is 0. Okay, which is this guy. We have said this is 0. Okay, and we know the margin of error. Okay, so this prediction error have a confidence interval, right, with mean 0 and based on the margin of error like this. Okay, now you don't want this interval for this one, right? You want the interval for y0. Okay, what you do is you add this term here and add this term here. Okay, so that means that this will be distributed as this plus this guy. Okay, so if you want to predict the individual response, you also have the same point estimate, okay, which you should expect, but the margin of error is larger. Okay, so what remains is to show you this guy. I will just do it in 10 seconds because it's very fast. Okay, and turn out that these are independent, which we don't prove, but with some of these two, and this we have shown this guy, and this have variance of this, so we're done. That's how come you have one extra term here. It's coming from the fact that because you estimate the individual one, so that's why we have one here. Okay, so I'm not going to go further because we've done all the slides. Okay, just to remind you that first day we don't have class. Next week we have the quiz and also we have Q&A. And that's it, then we will have a test. Thank you. I'll see you next week. Bye-bye. I'll answer any question you may want to have. So homework 5 will be uploaded it will be due at the end of the semester, just to remind you. I will send everything by email, sorry, by Blackboard. Put it on Blackboard, the announcement day. So stay around, answer any question you might have. If you have, please feel free to ask. I guess we only have 10 people here.